In yesterday's video, we learned about hydrocarbons. In today's video, what we are going to do is learn specifically about how to name alkanes. Alkanes are the family of carbon atoms, or excuse me, family of hydrocarbons that have just single bonds. And you're going to learn that the name of the alkane will change depending on the number of carbon atoms present in what we are going to call the parent chain. The parent chain is the longest continuous chain of carbons that we can see. Now, those carbons, if we make a homologous series, for example, of all the alkanes, you'd have methane, ethane, propane, etc. Those would be called a normal alkane. In the homologous series, those differ by 1 CH2 unit. So for example, if you have CH4, which you're going to learn is called methane, versus C2H6, ethane, and C3H8, propane, if you look, each one of them has they differ by CH2. So how do these things get named? Well, all of the alkanes will end in ANE. So when you see the suffix ANE, you know that it's a single bond. The prefix that you're going to give it will indicate the number of carbon atoms in the parent chain. And you may want to write that part down, in the parent chain. We'll talk about what a parent chain is in a second. The continuous chain is not, or the continuous parent chain is not necessarily a straight line when you build them. They actually, if you remember last year using the model kits, you might remember that the carbons zigzag when they make single bonds because they're making a tetrahedral shape, something like this. However, this is really messy when you're drawing it on paper, so we would tend to draw that. Instead of zigzagging it, we would tend to draw it just as a 5-carbon chain, as a straight line. It doesn't look like this in reality, but that's easier for us to draw. So, in order to successfully name alkanes and any other compounds that we're going to deal with, you need to start right now memorizing prefixes. These prefixes that are listed here, meth, eth, prop, bute, pent, hex, hept, oct, non, and dec, are all prefixes that you're going to use a lot when naming alkanes and other compounds as well. The 4 confusing are the first 4. They don't make a whole lot of sense, but the rest should be reasonable. So start working on memorizing those. Maybe make flashcards if you need them, but most of you will do okay with these if you just set aside a few minutes to work on them. Now, the rules for naming alkanes you have, and I'll try to give you examples as we go through just to show you what I'm talking about. So the first rule is to find the longest chain and use that as the base name or parent chain of the compound. Now, you have to be very careful because the longest chain may not always be drawn as a straight chain. What I do is I try to find the longest carbon chain I can without picking up my pen. So something like this. If you look, if I start on the left-hand side, I can make a chain through 4 without picking up my pen. And I could also do it the same way. That's also the same parent chain. Even though it looks different, they both are 4 in the parent chain. So in that case, I would want to look at 4. That prefix is bute, and I would use that as the parent prefix. Moving on to the second, we can attach things to that group called substituents. So if we go back up and look at this, if we say our parent chain was the red line that I have drawn in, it could have been straight across. This is an attachment to the parent chain. We would call that thing a substituent. Now I'm leaving off the H's for simplicity right now, but you'll see what I'm talking about as we go. Then the second step is to number the carbon atoms, starting with the number 1, finishing all the way through the parent chain only, but you always want to put the number 1 closest to the end that has the substituent. So you'd want to make sure that it is numbered in a way that the substituents would have the lowest number. We'll show you what I'm talking about with an example in a minute. Then what you want to do is name and give the location of each of the substituents. And if you have a substituent or a group that is hanging off the parent chain that has 1 carbon in it, it is called a methyl group. If the substituent has 2 carbons, it would be an ethyl group because of the prefixes meth meaning 1 carbon, eth meaning 2 carbons. The fourth rule is that when 2 or more substituents are present, you would list them with their carbon number in alphabetical order. So for example, if there were an ethyl group and a methyl group off of a parent chain, ethyl would have to go before methyl. Whatever number ethyl has, whatever number methyl has, you would say that. So say it could be like 2, 3. 2 ethyl, 3 methyl. The prefixes, if you have 2 of the same group, let's say you have 2 methyl groups, you would say dimethyl, but you would have to have 2 numbers to indicate where both of them are. So it could be 1, 2 dimethyl, and then whatever the parent chain is. If you look here on the step 4 in red, it does talk about the name of the number of the location, whatever the branch of the substituent is, and the name of the parent chain. And just as convention, we generally use commas between the numbers and dashes between numbers and words in properly naming a compound. I'll show you exactly what we mean by doing a practice example. Now, you may want to watch through this first practice example to see how it works. But if you're really brave, you could hit pause right now and try it on your own. If you're ready to try it, however, what you want to do is find the longest parent chain. Now, this takes practice. A lot of students will mistakenly identify this as the longest parent chain because it's the one that's drawn straight across. However, if you look, that only has 1, 2, 3, 4, 5 carbons in it. You're looking for the longest continuous chain. You may notice that if you turn and go down on this carbon chain, you can actually get more carbons. 1, 2, 3, 4, 5, 6 carbons. So when I'm naming these, what I always do is draw right on the compound. I draw a line right through the longest chain that I can find. Then my second step is to circle the substituents. Anything that isn't in the parent chain is considered a substituent. So that CH3 group and this CH3 group are considered substituents. Now, you want to name those substituents, or excuse me, you want to number the parent chain so that those substituents have the lowest possible number. You can always start at one end. One possible naming system would be to call this carbon number 1, 2, 3, 4, 5, and 6. And the opposite possibility would be to call this one 1, 2, 3, 4, 5, and 6. Now, you want the numbers that the substituents are assigned to be the lowest possible numbers. If you look at the green numbering system, this group would be 5, and this group would be 4. So we'd have a 4 and a 5. However, if you look at the red numbering system, you would have this group being a 2, and this group being a 4. We want to choose the 2 and the 4 because that is the lowest possible numbering system. So you can erase your green numbers, and now you are ready to put the names together. These groups, this is called a methyl group because it has 1 carbon, and this one is also a methyl group because it has 1 carbon. They are located on the 2 and 4 carbons. So we would say 2, 4 dash dimethyl to indicate that there are 2 methyls. One lives on the 2, the other lives on the 4. Our parent chain has 6 carbons in it, so that's hex. And because they're all single bonds, we end it with ane. So the name of this compound is 2,4-dimethylhexane. What I would like you to try to do is next draw a structure for 3-ethyl-2-methylpentane. Now, if you're brave, pause the video and try it in pencil right now. If you want to see the answer, you can try along right away. My suggestion is to always start at the back of the name. You know that your parent chain is going to have 5 carbons. So I would draw your 5 carbons. Now, count them. You can start from left to right if you'd like, although you could do it the opposite way as well. 1, 2, 3 carbons over, you are going to put an ethyl group. Ethyl means that you have 2 carbons. So I'm going to say CH2, CH3. And that's coming from the fact that this carbon here, if you were to draw out what it could bond to, it's already making 1 bond to a carbon, and it has to bond to yet another carbon, 2 carbons, to make it an ethyl. So there's only room for 2 H's on this first carbon, and there are room for 3 more on the last one. Then on the second carbon, you can draw a methyl group, which is just 1 carbon with 3 H's. Now, the rest of the compound can be filled in with H's. Remember, every carbon can make 4 bonds. If you look at your carbon number 1, it's already making 1, so there are room for 3 more hydrogens. This carbon's already making 3 bonds, so there's only room for 1 more hydrogen. This one's making 1, or making 3, so there's room for 1. This one has room for 2 more, and this one has room for 3 more. Now, you could draw all those H's out in their exact positions, up and to the side and to the bottom, or wherever they would go, but it gets a little bit cluttered, and this is what we would call like a condensed form, and I think this is the easiest way to represent that compound. Now, organic halides are very easy to name as well. They're named just like alkanes would be. You'd follow the same set of rules, but instead of being a methyl or an ethyl group as a substituent, now you have a chlorine, a fluorine, a bromine, or an iodine as a substituent. And you use the prefixes fluoro, chloro, bromo, and iodo as their abbreviations. So again, if you want to pause the video and try drawing this yourself, you certainly can. Otherwise, try drawing the structure for 1,2-difluorobutane. Again, start at the back of the name. Bute means 4 carbons. So draw yourself a skeleton structure of 4 carbons. And then on the 1 and 2, you are going to put fluoro groups. Now there's only 2 fluoro groups total. One of them lives on 1, the other one lives on 2. It does not matter where you put them, top, bottom, wherever. I just am drawing them on the bottom because I have room here. Now, you could draw the rest of the H's in their exact positions, but if you look, this end carbon, number 1, has 2 more H's that it can bond to. The next carbon only has 1 more H that it can hold. This one has 2 more, and the last one has 3 available. So that is how you draw the structure for 1,2-difluorobutane. Now, cycloalkanes are alkanes that form rings, meaning instead of a straight chain, you would loop back and connect the carbons in a ring structure. To name them, you use the prefix cyclo to indicate that it is a ring structure. So instead of saying propane, you would say cyclopropane or cyclohexane, etc. Substituents are numbered the same way you would. However, if there's only one substituent, we'd call that carbon number 1, and there's no reason to say it. I'll show you an example. If we were to do this practice problem, and if you want to pause these and try them on your own, you certainly can. This first one, where there are 3 carbons in the ring, if you look at that, there's 3 carbons. 3 carbons prefix is prop. Now, because each carbon is making 2 bonds already to another carbon, there's only room for 2 H's on each one. So we know that they're all single bonds, so we'd say propane. But it's in a ring structure, so we want to add the prefix cyclopropane. You could write that all as one word. This one has 4 carbons, and it's in a ring structure, so we would call this cyclobutane. Now, the next problem says to draw a structure for 1,3-diethylcyclohexane. And so if you were to do this, you would want to start at the back of the name. Hex means 6 carbons. So you would start with 6 carbons, but since they're cyclo, you want to put them in a hexagon, like this. And then it says that on the 1 and the 3 carbon, you are going to add an ethyl group. 1 on the 3, 1 on the 1. That's why diethyl, 2 ethyl groups. Now, it does not matter which carbon you call 1. Let's pick the top carbon to be 1. An ethyl has 2 carbons. An ethyl group is a CH2, CH3. Sometimes you will see that written as C2H5, just shorthand. So I'll do that in blue here. I will write CH2, CH3. Now, if this is carbon 1, then I could go to the right, like around a clock. This would be 2, and this would be 3. And I would add yet another ethyl group. However, I could have gone counterclockwise and picked the carbon right here, and it wouldn't have changed anything. Now, chemists are really looking for shorthand. And so one of the things that you might see done in your books and in other resources is that they will use line notation to indicate these things. So to a chemist, a triangle is an example for cyclopropane. Each point represents the carbon, and it is understood that there are 2 hydrogens that come off of each point. For cyclobutane, we would draw that as a square. Each point again represents a carbon, and it's understood that 2 H's are coming off of each of those points. In the case of this 1,3-diethyl cyclohexane, we would draw ourselves a hexagon. It's understood that each of the points each of the points is a carbon. And if we want the substituents to be drawn, now we have to draw them. So here I would show CH2, CH3, and CH2, CH3. One on the 1, one on the 3. These are the same structures. Now the only thing that's missing in my blue structure is the additional H's. So if you go through and you look at each carbon, remember each carbon can make 4 single bonds. 1, 2, 3, we're missing 1 H. This one's missing 2. This one's missing 1, just like its partner up in position 1. 2, 2, and 2. So the blue structure is now identical to the black structure. And that brings us to the end of naming alkanes. If you are looking for more information, you could search online or read your book and do some of the practice problems in the text, but that pretty much should get you through it, and we will cover this in class tomorrow.